Yeah, so welcome student for today's class. So this course is MA425 Topology. Okay, and this is lecture number 2. Okay, so recall that yesterday, rather in our last class, we discussed about the basic introduction to topology. What do you mean by topology on a set? Okay, with lots of examples. Now today we will further study topology with the help of some smaller set. For example, if you learn linear algebra, you must have learned that something called idea of a basis, right? We generate the full linear space, okay, in a unique manner. And obviously you remember that the number of the basis may be different, maybe may not be unique, right? There may be more than one basis for a linear space. Similarly, for topological space also, you can define something called base or basis. People say both of a topology, right? Okay, so we will discuss first the definition. What do you mean by a base of a topology on a set X or basis of a topology? You can say both. Okay, so what is the definition? So let us start with the definition. So definition. So let X be a set. Okay. A basis or a base, whatever you write down, for a topology. I will define how I will discuss how you can define the topology. First, let us define this base topology. For a topology on X, you can ask what do you mean by that topology, that we will define it. Okay. So what is this? This is a obviously kind of subcollection. So let me write down this symbol script B. So this is obviously subset of this power set of X. Okay, like to topology, but this is kind of a smaller set than topology. Okay, in the smaller collections. So subcollection B of these. Satisfying following the condition. Okay, so what are the conditions? Satisfying the following conditions. So what are the conditions? So first conditions is 1. So that B covers X. What does that mean? That means that if you choose any element of X, you can find out the element of B. Okay, which contains the element. That is for any X belongs to X, there exists B in script B such that the X is an element of this B. This is the meaning of B forms a cover. Okay. This is one point. And second point, which is most important, point number 2, that if you have X, X belongs to intersection of 2 elements of script B for some B1, B2 belongs to the script B, that collection, then there exists another element B3 belongs to the same collection such that what happens is that X is an element of this B3 and the B3 is sitting inside B1 intersection B2. This is the most important What does that mean? That means every element which is inside the intersection of any two basis element, there will be a third basis element which is also element of which is also contains that element x, but this is inside the intersections. Okay. So you understood that meaning of things so far. So so whenever you choose for this cover the whole thing, and whenever you choose, then you will have something sitting inside that thing. Okay. So maybe we will start with some examples, then I will give some theorems, important theorems. So we'll start with some examples. Now you recall that discrete topology which we discussed in last lecture. So discrete topology. What was that? So given a set, and what was a tau? Tau was nothing but the power set of x, right? But this is too big thing, right? So instead of that, if I choose my B is all singleton set x. Okay, x belongs to x. So obviously these singleton sets, you see that these singletons are also element of tau, this set as I said. Not only that, they forms a base. What does that mean? That means that if obviously you choose this covers the union of all those elements cover x, because you are writing all the open singleton points or open sets here. Okay. And not only that, if some element, see the intersection of any two such thing is empty, right? So the second condition is vacuously true. So this forms a base or basis, whatever, for the discrete topology tau. Okay. Okay. Now maybe I can give some more examples. So example 2. Now you recall that I think we have some 1, 2, 3, and one topology was defined by these and these and these, right? And now this is a topology on X, and then you can define a basis for this topology, obviously just containing this. See, this forms a basis. Okay. Obviously so these are the element of basis are open sets. Okay. So whenever you choose element of x, okay, 1 minute there. Okay, so I define the topology for x is by covering, right? So this is on x, yeah. So this is the basis, 0, 2, and x, yeah. This will be a basis for topology tau, because see, this covers the full thing. Not only that, if you choose any element here, 1, 2, 3, you have element which contains this. And not only that, if for example the element 1 is belongs to this and this, and you see that 1 is there contain, like, so 1 is element belongs to this intersection x, is actually 1 is belongs to this set, which is open set, and is also element of this, right? So satisfy these conditions. Okay. So and then one more important example I should discuss, that Euclidean topology on R, or standard topology, whatever you say, standard topology, standard topology on R. Okay. Now what was the standard topology? So tau was the collection of all open sets in R, right? All open sets. Now we can define a base or basis for this tau, and this my basis is what? This is collection of all open intervals, all interval of the form A, B. A, B such that A and B are real numbers. Okay. And now you see that this is a basis for the usual topology. Okay, this is a basis for the usual topology, and obviously you can check why it's basis. Okay, and obviously I will come to the point how we can generate the full topology from the basis in a minute. But to check this basis, it is obvious that this B covers R, first point, and number two is that if you have element X is element of something, say A1 B1 intersections A2 B2, then what does that mean? That means there is some intersection, right? So that means, so this implies what? This implies that A2 is less than B1, and hence you can say that your X is element of A2 comma B1, which is inside this intersection, right? B1 B1 intersection A2 B2. Okay, so here basis elements are open intervals, and given any two open intervals, either they intersect emptily, means the intersection is empty, or the intersection is again intervals, and see the intersection is intervals A to B1. Okay, this is the case only, possible case. Okay, so this is that basis for the standard topology on R. Okay, there are many other topology on R, maybe I will come later, but before that let us first discuss how to generate topology from a basis. Okay, so the question, this is a very important question, that how do you generate a topology from a basis, from a basis. Okay, so how to generate? So if you know a set and a basis, means a subcollection of power set of subset power set of that set satisfying these two conditions, then what will be the topology on that thing? Like, what are the all open sets you want to know? Okay, now the answer is to these things. So you generate this by like this. So the topology tau is defined by this, all those sets of subset of X which are open sets, such that for any X belongs to U, there exists B belongs to, so it's capital B is given, the basis is given, B belongs to B, such that X is element of B, and not only any arbitrary things, the B is sitting inside U. Okay, so you collect all those U's. Those U's are actually, so inside U you can find out a basis element which contains X. This is the meaning of this collection. So you collect all the U such that every element of U, for every element of U, inside the U you have a basis element that contains that element of U. Okay, so these collections actually forms a topology on X whose base is B, that script B. Okay, yeah, script B. Okay, maybe, yeah, let me write them properly. Okay, now obviously when you claim something, you require a proof, right? Why this kind of collection is a basis at all. So that means you need to prove that it satisfies the three conditions of a, so why this collection is topology at all. So you need to say that it satisfies the three conditions of the topology. So what is given? Is given that this collection B is a basis for a set X. Okay, on some topology. Okay, Now how do you check that this collection which you are generating from the base B is forms a topology? You need to check the three conditions, right? Now let us check the three conditions. So what was the condition number one? That the empty set and the full set has to be element of the topology, right? So now, so if U is phi, then what happened? Using this formula, using this condition, can you say that U belongs to that phi belongs to this topological space? And this is obvious, right? Because for U in phi, there is no element, right? There is no element inside phi, right? So this condition is vacuously true, right? This is vacuously true, right? So the condition is trivial or whatever, vacuously true, you can say. Okay, if U equal to X, if you check the full set X, can you say this is open set? And obviously, because by definition of a base, whenever you have an element of X means what? So if U equal to X, then as this B is a base of X for any what happened for any small x belongs to X, what do you have? There exists, you can say something Bx belongs to this capital, the script B, such that what happened? Such that that contains X, and not only that, this is a subset of capital X. Okay, so this is obvious. So this implies that X is an element of the topology tau. Okay, so the first conditions satisfied by this collection tau. Okay, now second condition, you remember second condition, that it is closed under finite intersection, right? Now to prove the closure property with respect to finite intersections, it is enough to check for 2 only, for 2. Why? Because other thing you can do it by induction, right? As otherwise, so as why? Because you can, if you choose any finitely many okay, so let me write down properly here. If you choose any finitely many such elements, that you can write down as the first n minus 1 many elements as something, some U dash and the intersection UN, right? So U dash is this first n minus 1 many elements. So if you do it for 2 such sets, you are done, right? So let us do it for 2 such sets. Okay, so what we need to prove? We need to prove that given any 2 elements inside that collection tau, then the intersection is again an element of tau. How to prove that? So let U1 U2 belongs to the collection tau. Okay, U1 U2. So what is the definition of that collection? That whenever you have that element, that for any such okay, I will come back. Okay. So this is given. So now what we need to check? We need to check that the intersection U1. So this claim. Okay, so we will start from next line. So my claim is what? So claim that u1 intersection u2 is again an element of tau. This is my claim, right? Now to check that u1 intersection element of tau, what did you check? So let you check, start with an element x, which is the element of u1 intersection u2, and you check that every element of this is element of so if for every element of this you have an element of the basis element b which contains x and they are inside the intersection, right? Then you are done. Now if you choose this, so this implies x is an element of u1 and also x is an element of u2, right? But if as x is element of u1 and you know that u1 is element of tau, so there exists some b1 belongs to this b such that x is element of b1 which also contains in u1, right? Similarly for here there exists some b2 which is element of b again such that x is element of b2 which is a subset of u2, right? So x is inside both b1 and b2 and hence x is inside b1 intersection b2 which is again inside u1 intersection u2, right? But you know that b is a base. As b is a base, then what does that mean? That means there exists another element b3 such that what happened? Your x is element of b3 which is inside b1 intersection b2 which is inside b3 which is b1 intersection b2 which is inside u1 intersection into. So u1 for any element into you have an element b3. So this implies u1 intersection u2 is element of the topology tau. Done. This is the proof, because this topology contains all those subsets such that for any element of the set you have an element of basis element that inside the set and contain the element, right? So this is exactly satisfying the same condition and hence this is element of that. Okay. Now the third condition, that arbitrary union. Okay. So now you choose arbitrary union of sets. So let you have some u alpha belongs to lambda be an index family of elements of tau. Okay, now you need to find out that the union is also element of tau, right? So we need to check that so claim, what is my claim? That the union, so let me write down, this is u, this is union u alpha belongs to lambda belongs to tau. This is my claim. Now again, what you need to check? You need to check that for every element of u you have a basis element that contains the element which is inside the set u, right? So let you choose an element x belongs to u, this is arbitrary. Okay, and then there exists u alpha such that x is inside u alpha, right? Because u is the union of u alpha, and if some element belongs to union, so it must belong to one of the element, right? So x is the element of u alpha. Now once you know x is element of u alpha and u alpha is element of tau, so there exists some bx belongs to b such that what happened? Your x is inside that set bx, which is a subset of this u alpha, which is also inside u, right? So u contains that basis element, that b. So this implies u is element of that collection tau. Okay, so thus tau is a topology on x, right? So this is the proof that this collection is always forms a topology, and the basis which I defined earlier, this is the basis for the topology tau, right? Now question is that do we have a simpler way of defining this set, this topology, or equivalent way of saying this thing? The answer is yes. So you can do it you can play the game in some simple forms, right? So equivalent form, you can say that. Okay, so let me write down that proposition, which will gives you an equivalent idea of defining a base topology from a basis. Okay, so proposition. Okay, so again, you start with the basis. Okay, so let me write down properly. So let X be a set, and tau be a topology, some topology on X. Okay, and let this script be a basis or base for tau. Okay, then what? Then tau actually is a nice thing. So tau you can represent. See, obviously you learn how to generate tau from B, but it has a better representation. What is that? Then this tau is nothing but equals or equal to the collection of, you choose all the unions and take the collection. So collection of all unions of elements of B. This script B, elements of script B. Okay, so what does that mean? That means every open sets can be represented as a union of some basis element. This is the meaning of that thing, right? So on the other hand, if you give me a basis tau, then how do I generate the topology? I will take all kind of unions from that set, whatever union is possible, arbitrary unions. Okay, so it can be finite number of elements set, finite number, counter number set, infinite number of set. Okay, empty collection, everything you can do, and this collection gives me the topology, and that topology is that topology for which this is the base. Okay. So one way of generating topology you learn that you take all the sets subset of X such that if for every element of X you have a basis element containing that element, right? On the other hand, right now I am saying that it is not only that, you can also say that the open sets are union of some elements of basis. Okay, now how to prove this thing? So you require a proof, right? So proof. So this kind of, you are saying that this kind of infinite connection, right? So this equals to collection of union of this. So first of all, you need to check that if you take a collection of union of this, that is inside tau, and the tau is inside this, right? So let me write down. So let tau dash be the collection of all unions of some elements of B, that B, right? So what is our claim? So what do we need to prove? We need to prove that your tau and tau dash are same, right? Now which one is obvious? Can you tell me? So this one part is obvious, right? Tau dash is subset of tau is obvious. Why? Because see, this is first part, that tau dash is subcollection of tau, right? It's obvious because what is tau dash? Tau dash is collection of all unions of element of B, right? And also you check that if this B is actually subcollection of tau, right? Because every element of B is also open sets. They actually true. So what does that mean? That means you are taking tau dash is element of tau and take the in the union, right? But tau is topology that closed under all the unions, right? So this is obvious. So it's trivial, this part. This part is trivial, as tau is closed under arbitrary unions. right? So tau dash will be element of tau, a subset of tau, right? Now conversely, the converse part, I need to check that tau, every element of tau is an element of tau dash. So let conversely let u is element of tau, right? So we need to check that u is element, u can be written as some union of element of tau dash, some union element of the basis. Then it is element of tau dash, right? And now because u is element of a dash, then for any x belongs to u, for any x belongs to u, there exists this bx belongs to that basis such that such that x is an element of this bx, which is inside u, right? So thus you can write down u equal to union of vx and x belongs to this bx. Okay, so you choose any element of u and then you take that basis element bx and take the unions. So this will be the full set u, right? So what does that mean? That means u is element of tau dash, right? Because u can be written as union of basis elements. So it's element of tau dash, and thus tau is also a subset of tau dash, right? Which proves that tau and tau dash are equal. So what does that mean? That means if you have a basis and the topology handled by the basis B is nothing but the union of all elements of the basis, union of all, choose any union of any collections, that will form the topology. Okay. So this is the how you can define the topology of the thing. Now the natural question is the converse part. So converse part is what? So given a topology, so given a basis, you find out a topology, right? Now conversely, the question is that given a topology, can you say about a basis? Can you say something is a basis or not? The answer is yes, and you can have the following theorem. So let me write down the theorem. So what is the following theorem? The following theorem tells you that when you know the topology, you can also find out a basis. Okay, so let this be a topological space. Okay, and suppose you have a collection. So you have a sub collection, something like that. Script C is a collection of open sets. Okay, so open sets of x. What does that mean? That means that is, this is inside this tau, subset of tau. What kind of collection? Such that what happened for each open set, for each u belongs to tau and x belongs to u, for each such thing there exists some c belongs to that script C, such that your x is contained inside C and the C is subset of U. Okay, this is the condition. If this is the case, then under this case, then this script C is a base for tau, same tau. Okay, see, base can be may not be unique, so there may be more than one base. Okay, but in this case this forms a base. Okay, so see the previous theorem was telling that how we can, from a base you can go to topology, how topology look like. Now here topology is given, you need to find out the base, how base can be then, right? So if this property satisfied, then it forms a base. Okay, So to check something a basis, what you need to check? You need to check that two conditions, right? So proof the two conditions. The condition number one was x and the full set x, and that empty set is a element of okay. So condition one is that that C collection C covers X, right? And that is obvious. Why obvious? So so you know X is a open set, so X is the element of tau, and then for any, obviously from the hypothesis, for any collection C, for any open set U. So if you choose U equal to X, then what happen? So suppose U equal to X, then what happen? Then for any X belongs to X by the collections, so you'll have directly C belongs to C such that X is an element of C, which is an element of U, right? And and then that is X, right? So inside X you have element of C which contains X. And what does that mean? That means that I mean, this is the condition that you have an element of C which contains X and inside X, right? So this is the first condition satisfied. Okay, and second condition was what? Second condition was that condition number two was what? Suppose X is element of some C1 intersection C2, where C1 C2 element of this gives C. Then you have an intersection element which contains inside that element, right? But C1 intersection C2 is an element of C. So what does that mean? And C is element of tau. C is inside tau, right? So C1 C2 C1 C2. This implies that C1 C2 belongs to tau, right? And this implies that C1 intersection C2 C1 intersection C2 is also element of tau, because tau is closed under finite intersection, right? So this is C1 intersection C2 is also open set. Clear? Now when you have an open set inside tau, and then the condition tells you that now you choose X equal to these intersections. Okay, so you can choose your U equal to this intersection C1 intersection C2, right? So for this U, what happened? For these and X belongs to C1 intersection C2, there exists some C3 belongs to C, such that what happened? Your X is element of C3, and which is a C1 intersection C2, right? And done. So this is the second condition of the basis, right? So this implies that this collection C is a basis. Okay, now question is that whether this basis is tau or not. So this is basis for some topology, right? Now you can ask how do you know this is the same basis, this is the same topology that C generates. Okay, so for that, so let us let some tau dash be the topology generated by this collection C. Now so our claim is what? Our claim is that these tau and tau dash are same. And again here also one part is obvious. So here this part is obvious, right? So the part one, so check that tau is a subset of tau dash here. Why? Because if U belongs to tau, it's open set, and you choose some element X belongs to U, then there exists C belongs to this script C, such that X belongs to C, which is subset of U, right? Clear? So this is from the property of what is the given property that. Okay, so what does that mean? That means U is all those sets which contain X and it contains an element of C, right? So this implies U is an element of tau dash, because tau dash is a topology generated by C, right? I define two ways how to define topology generated by and basis element. The first one is this, right? So what does that mean? That means your tau is a subset of tau dash. Okay, this is okay. So whenever you choose an element, a subset U of tau, an element X of U, obviously by the condition there will be a element C of script C which contains X and inside U, right? And that is the meaning that U is element of tau dash. Okay, now conversely what happened? So conversely you can say that conversely so let you choose another element, say V is element of tau dash. Okay, so I need to check that V is element of tau, right? But you know that tau dash has another expression, right? Tau dash can be written as union of elements of so some kind of union of elements of C, right? So you can write down V is nothing but some union, some arbitrary union of C alpha and lambda. Okay, where C alpha is element of C, right? Clear? And now so now you know that these C alphas are what? C alphas are open sets, right? So this is alpha also element of tau, and tau is closed under arbitrary union. So what does that mean? That means this implies V is element of tau, right? So what does that mean? That means every element of tau dash is element of tau, and which is finally you can say that this implies tau, the topology tau and topology generated by C tau dash are same. Okay, so this is a proof that given a topology on a set X, you can define a subcollection to a basis for the topology or base for the topology. Okay, so now natural question which comes into our mind, that the natural question which, okay, maybe I can stop here because this is a new subject and you may need to time for digest. Okay, so so I will stop here and we will start the new idea from our next lectures. Okay, let us stop here.